Hello, my name is Mark Banish. I'm president and chief scientist at Neoterracon, a nanomaterials consultancy located here in New Hampshire in the United States. I wish I could be with you in Barcelona today, but unfortunately, some recent ill health has restricted my ability to travel. But I am grateful for the opportunity to give my presentation in this fashion. I'm going to be talking today about thermogravimetric analysis of carbon nanotubes, specifically within the context of what they can teach us about the material and how that learning can apply to what type of applications we should do. But I want to give this disclaimer first. As it says here, I am just going to provide data, evidence, and theory that are related to the reliable industrial production of carbon nanotubes. I'm not making any claims about suitability or superiority of any material for a particular application. So this is going to be a case of where I'm not going to tell anyone that their baby is ugly, as we say here in the US. So let's get down to it. Carbon nanotube basics. The taxonomy recognizes three forms. Single wall tubes, which are exactly that. They're the smallest of the three types, with diameters between 0.7 and 2 nanometers, typically. Most importantly, you get metallic single wall tubes and semiconducting single wall tubes. And that's probably the most important thing about this tube type is understanding what type of electrical conduction you're going to get out of it, because the semiconducting are one thing, but the metallic can be as high as copper. So you're getting a carbon-based material that has metallic-like electrical conductivity. Dual walls are the next type, and they're exactly that. Dual walls really aren't investigated that thoroughly because they're generally not formed except as a side product with single walls or in the production of the next type of multi-walls, which are exactly that. These are tubes that have multiple walls around them, 5, 10, 15, commonly observed. They're the easiest to make, and they're also the easiest to obtain commercially for a reasonably low price. You have graphitic spacing between the walls, and diameters are generally above 2, with 5 or 10 nanometers being fairly common. Again, why use nanotubes? Well, they have a high thermal conductivity. They have a high electrical conductivity. One thing which I find particularly useful is their elongation to break. It's 6 times that of a carbon fiber. As people who worked with carbon fibers will know, that's only about 1%. So you're able to stretch a fiber made out of nanotubes 6, 7% before it breaks in some cases. They have a very high tensile strength. They're highly flexible, even at cryogenic temperatures. So if you want something that's going to work in space and remain flexible in space, nanotubes might just be the material you want. And also they have a very low coefficient of thermal expansion. So if you're building a composite and you don't want the material to delaminate when it's exposed to different temperatures, nanotubes make a pretty good material choice. So let's go back about 20 years. And in the year 2005, there were following major manufacturers of nanotubes. Single walls were made primarily by a company called CNI, Southwest Nanotechnology in Oklahoma, Thomas Swan in Consett, UK. These were the companies that were the major manufacturers of single walls. Multi-walls, you may recognize their manufacturers. It was more typical chemical companies, Arkema, Nanosil, and Bayer. Nanosil is right now the only one of these companies that, to my knowledge, still makes multi-wall nanotubes for their own sake. None of these other companies make a standalone carbon nanotube product any longer. The future was bright back in 2004. If you look at CNE News, you'll see that by 2014, they forecast we'd have over $1 billion in this market. What happened? This never came about. Well, there were a couple of reasons. First, there was no scalable process. Some of these processes were, shall we say, thermodynamically limited. There were no good analytical methods to determine suitability for purpose. A lot of times they thought they'd be making tubes that had metallic conduction, and they didn't get metallic conduction. There was poor adhesion in composites. There was no joining between, say, a thermoset resin and a nanotube surface. And since I'm going to be talking today about TGAs and surface chemistries, well, you can understand why TGA might be relevant here. The tubes also were short. They were typically under 5 microns in length. And experience has shown that longer tubes, things that are 100 microns or longer, up to a millimeter or so in length, are the preferred embodiment for most types of applications. Finally, at the time, there were few applications. This is most notably because of the high cost. $500 a gram was simply beyond the pocketbook of many application developers. And there was a build it and they will come. Sometimes people built factories around processes because they thought they were going to be able to sell the product. And in the end, the process did not lend itself typically well to a scalable process, and all that capital, unfortunately, was for naught. Well, let's see what we're talking about, because seeing sometimes helps people put these things in perspective. We are visual creatures. If you take a look here, these are SEMs of a typical multi-wall nanotube product. These tubes have lengths in the millimeter range. And if you look on the one side where you see the measurements, you can see that these tubes are long, fairly straight, and have diameters in the 3 to 8 to 10 nanometer range. So these are a fairly typical multi-wall product with the right size diameters. But note the structure, note the morphology. Note that these things are straight. But if we take a look by just changing the synthetic conditions a little bit, what do we get? I call this the pasta model. We see we can get different morphologies. We can get tubes that look like ramen noodles. We can get tubes that look like linguine. All of these things are possible with just small changes in the synthetic conditions. And since those small changes in the synthetic conditions can occur within normal variability and variation within a process, you might be getting different tube types at time 1, and you do it time 10 or time 11 or whenever. So this just gives an idea of what we're talking about when we're talking about varied material in terms of the changes that one actually is seeing in the base underlying structures. So we need characterization. Well, what do we do to characterize these things? There are 3 families of techniques. First is spectroscopic, the second is imaging, and the third is thermographic. Spectroscopic is Raman and X-ray fluorescence, which give information about tube order, material composition, whether there's residual catalyst or things like that in the material. This technique only looks at a very small area. I mean, laser beam in something like a Raman spectrometer is very tiny. So you're only looking at a very small part of the material. It's somewhat akin to the old fable about the blind man and the elephant. Are you really sure that the elephant is long and skinny like a snake, or is it really wide and round like a tree trunk? Well, by looking at one area, a small area, you're never quite sure. And that's the same thing with SEM and TEM. You get these wonderful pictures, but whether they represent the entire structure is another thing. This is why TGA, to me, is so useful. It's because we do need this reliable, unequivocal, and accurate method to determine composition and physiochemical properties. There are a couple of advantages in TGA. It's fast. It's relatively fast. It requires little calibration in the instrument or maintenance. It's generally immune to operator bias. You just put the stuff in there, turn it on, and walk away. It also requires a small sample, a few milligrams, but you can run multiple samples completely automated and get an idea statistically whether what you're looking at is truly representative of the product. There's one disadvantage, and that is their clear interpretation of the results for real materials. Here's an example. This is a TGA of NanoSil 7000, which is a multi-wall product, and you see 2 curves. The first curve in blue is the weight loss as the material is heated, and then you see the derivative of the weight loss in black, and this looks like a fairly homogeneous material with a single component. Looks very neat and clean. Kudos to NanoSil for producing this. But here's an experimental product made by a different manufacturer, and you see you get a completely different curve shape. There's obviously more than one component in here, and the question is, how many components are in here? Well, let's talk about modeling that and finding to figure out how many different types of distinct carbon species we're dealing with. So to begin with, we're going to assume the rule of non-interacting mixtures, namely that it doesn't matter how much of component one and how much of component two I have, but they're not going to interfere with each other when they combust in a TGA in air. We're going to use the Fraser-Suzuki equation to model the reaction kinetics. This equation has been used successfully with other carbonaceous materials, notably coals, to structure or understand the shape of the derivative curve. And we're going to test our model against two commonly deployed analyses. The first is Kissinger analysis, and the second is using something called the distributed activation energy model. Now, how do you fit these things? And if you want to look, there's a reference there to a paper I wrote in 2021 on how this whole thing can be done, but basically starts by expanding the Fraser-Suzuki function from that into something which is a little more computable. I agree it looks a little tedious, but believe me, it's much easier to differentiate. And when doing line fitting, you usually have to take the derivative of a function with respect to each one of the variables. So it may be tedious, but that's why we have computers. And in this case, I even wrote my own code in Fortran. Reason why is because I know what the code was doing. Often Excel, some people may have used some features in Excel and found out that you don't always get the same answer for the same data. So in order to make sure that didn't happen, I wanted to make sure I understood how the code worked, and that's why I wrote it in Fortran. So here's some results. We'll take a look at material 7,6 single wall tube, its derivative mass loss curve. If we take a look at this, we see that we can fit it to a single Fraser-Suzuki function or two Fraser-Suzuki functions. The one in red seems to be not as good of a fit as the one in green. So what is this telling us? How do we know what the heck's going on? This is supposed to be a single homogeneous material. That's what it says on the bottle. But statistically, this is what fits better. Two functions. There are two distinct carbon components in this, at least with respect to combustion. And we can extract these Fraser-Suzuki functions, and then we can apply Kissinger analysis. Kissinger analysis is a standard TGA equation used to extract out the activation energy for combustion and the highest point at which the combustion occurs. We also get the kinetic prefactor. It's very straightforward, very simple, and it assumes your standard kinetics. So if we take a look at that, we take a look at the first fit, the first equation fit, we get a pretty nice straight line. And we get a number for the activation energy and for the kinetic prefactor, which are typical for carbonaceous materials. And if we do it for the second one, we get a little poorer fit. But again, we still get numbers which are pretty good and certainly are representative of other types of carbon materials. Therefore, we have a fair amount of, I hate to say this, faith that these are reasonable physical values and may actually be those for the material. But let's take a closer look. And for that, we're going to use DAEM analysis. Now, in this, we're going to assume that there's not a single activation energy for combustion for each one of the species. Instead, they follow some form of distribution. In the original embodiment of this analysis, we assumed a Gaussian distribution. And you would simply measure the mass loss at a constant heating rate and do a line fit. Well, we're going to rewrite that. We're going to rewrite that and replace the time variable with temperature. And the reason for that is that most TGAs are run using temperature as the variable. We're also going to replace the limits from 0 to infinity for the activation energy with an experimentally based range. There's no such thing, at least to a chemist, of an infinite activation energy. Maybe there is, but not in this case. So we're going to close that down to a variable range. I used here roughly 25 kilojoules per mole to about 400 kilojoules per mole, which is certainly representative, again, of carbon materials. You do need to know the starting temperature alpha and the heating rate beta, but here I've replaced the distribution function with just a probability density. And we're going to solve for it. And we're going to use Gaussian quadrature because that's a very simple technique to implement. And here's an example of what you get. Here's that fit 2 for the SWIMP material. And you'll notice that we get a pretty good correlation between the mass loss curve and the fitted data. But the more important thing is the activation energy distribution. So let's take a look at this. You can see along the x-axis the various activation energies, and you see that we get something that doesn't really look like a Gaussian. I don't know what it looks like, but the expected value of the activation energy is 100 kilojoules per mole. That's different than what we had before. It's lower. Now, I'm not going to argue about why this is different, except the fact that let's remember that the Kissinger analysis is fairly basic. It just looks at a highly averaged value. This technique looks at a true distribution function, and we can see that we have a range of distributed values. And that's interesting because this is clearly not a homogeneous surface, nor is the other fit component. They have similar distributions, but they do not have a delta function. This is advertised as a highly pure, again, highly NIST certified material, and yet its surface is not homogeneous. So let's take a look at another practical application. This involves polyaromatic hydrocarbons. Now, why PAHs? And the answer is because they pop up all the time during CNT synthesis. You'll find them occurring during the synthesis of nanotubes, fullerenes, nanofibers, carbon black. Heck, let's not forget that fullerenes were first discovered in interstellar medium by Harry Kroto, and that out there as well, you find a lot of PAHs. So even out in deep interstellar space, where you find carbon nanomaterials, you find PAHs. They're perhaps the most common component in terms of being a contaminant, and they've been found at levels as high as 5 to 10% of mass. And they're also EHS hazards. They're carcinogenic. And because they absorb on the surface, they can strongly affect end product performance in things like composites. They're forming the interface between the nanomaterial and the matrix. Well, can we remove them? Of course we can with a technique called Soxhlet extraction. I'm working on this as a procedure for the ISO Technical Advisory Group 229. And in this case, you simply use methylene chloride, a Soxhlet extractor, and you follow along. And when you start analyzing, and I'll use 2-ball 75% single wall nanotube because this product is just, again, representative of what's available commercially. If you take a look, you will see that the GCMS of that extract shows that naphthalene and pyrene are the majority products. The pyrene is a little lower in concentration, but naphthalene forms a fair amount. As a matter of fact, the dominant amount of what you find in the extract. And if you run the TGAs on the control and the extracted material, you'll see that the shape changes considerably, as does what you find when you start extracting what's underneath of those using Fraser-Suzuki functions. Again, the control and the extracted, you see that one component seems to go away in the extracted. I don't know what it is, but I can tell you something that's very interesting about it. Here's the control. This is what was provided. This is what you get out of the jar. And if you put it in the TGA, this is what you get. I apologize for the eye chart quality of this slide, but I think you can see that the activation distribution, the activation energy distribution is a little bit all over the place. I do get different expected values for it for the 3 different fits to those components. But here's something that's really interesting. Here's the Soxhlet material. Both components reduce to the same activation energy. They have a different kinetic prefactor, mind you, but it turns into a single peak. Strip off the stuff, and you find a very homogeneous surface. There are other things you can do with TGA. You can monitor during processing or the effects of processing. Here's a material that I processed. You can see the controls TGA and the process TGA. This was a technique I did to try to induce greater amounts of order to repair things like stone whales, defects, and other things in the material. And again, when we process it, we get slightly different fits. And we can apply the EA technique again. And here's the control. We get a variety of activation energies with expected values of 188 and 198 respectively. But look what happens at the process stuff. It all shifts up. Shifting up, requiring a higher activation energy, suggests that the order that was sought to be introduced by the process has occurred, at least on some level. And I will say suggests rather than proves, because there's more work, obviously, that needs to be done. So what can we conclude? And the answer is that accepted kinetics models can be used with TGA to extract the number of carbon species present in a nanomaterial sample and the corresponding activation energy distribution. Kissinger analysis alone can be misleading because it gives an average value. It doesn't provide any information about the distribution. The data, again, showing that the distributions are not normal. Purified samples have a nice narrow range, but I'm not sure why those distributions are what they are. Removing contaminants is wonderful. It can actually show that what you've made is very good if you get rid of the stuff on the surface, and that you can see that processes designed to induce order actually seem to actually induce order, at least with respect to combustion. So you can learn a lot from just burning something. So thank you for listening. Thank you for just paying attention today and accepting the fact that I had to do this remotely. I do want to acknowledge the following people: Dr. Elizabeth Mansfield at NIST, who helps me with TGAs and understanding them; Dr. Rachel Stevenson at Huntsman Chemical, who does likewise; Dr. Glenn Irwin at Rice at their Carbon Hub, who provides me with data so I can analyze these things and learn more about carbon materials; Mr. Peter Antoinette, formerly of Nanocomp, who provided me with a great deal of financial support during this; and Mr. Paul Anzalone of Nanoproto. Paul is an excellent electron microscopist, and all the images that you saw here today were taken by him. So thank you very much for listening. I hope you found it engaging. And if you have any questions, please feel free to contact me there at that email address. And once again, thank you for your attention.